Hi everyone. Thank you for joining this session with the name Taming the VM Sprawl, KCP meets KubeVirt. Oops, sorry. So in the next 20 minutes, I will talk about a challenge which actually every team should face running KubeVirt at scale. How do we manage all the VMs without chaos? So I will outline two core challenges regarding that and will then introduce KCP and explain how it helps to solve the problems. And then I will show how everything connects in a short demo. My name is Sören Henning. I'm working as a software engineer at Kubernetes, where we focus on making Kubernetes clusters manageable at scale. With that, let's dive in and let me start to explain why we should talk about KCP here. So running KubeVirt in Kubernetes is only part of the story when we want to build a VM platform with multi-tenancy. Um, with that, we have two main challenges. The first is the challenge of multi-tenancy. So when we have a Kubernetes cluster with KubeVirt running in it, every consumer, regardless of their role, is sharing the same API resources like this. So they communicate to the same API server and sharing the same API resources. And we have also a very flat hierarchy of authorization with mostly role-based access control, so that we don't have any isolated context for a consumer. In the following, I will use consumer, but you can treat the consumer similar to a tenant in the end. Okay, so the second challenge is then the challenge of the cluster boundary. So if we want to run or we want to have multiple clusters behind our VM platform, which can be targeted by consumers, it gets even more complicated because we have no single surface of control for consumers then. Okay, with these two challenges or problems, we come to an idea to add a logical layer between consumers and KubeVirt clusters. Like here in the middle. For now, I will call it a tenant-aware API platform, and this should have ideally isolated context for each consumer with its own APIs and its own authorization. And a consumer should be able to use these APIs to create virtual machines in a Kubernetes cluster and also getting the state of the object then over via the tenant-aware API platform. And it should be also able, and the consumer should be also able to target multiple clusters. And this should also be the case for each other consumer or tenant. So like this. Okay, with that, we have a high-level overview of what we want to achieve. So now let me explain why we should still look at Kubernetes, even if we know that we cannot use Kubernetes itself to solve our problems. Because Kubernetes is still interesting as an API layer. So because it has already a strong foundation with major API conventions and existing tooling, which we could reuse, and we wouldn't need to recreate a whole API ecosystem for our approach. So, and therefore it's also consistent and easy to discover and easy discoverable. And last but not least, the Kubernetes API layer can also be easily extended via API aggregation or custom resource definitions, which would give us the possibility to add or remove APIs dynamically. But as mentioned in the beginning, we have two things which we cannot solve with Kubernetes itself. So because the APIs are cluster scoped, so everyone shares them, and we have only a single hierarchy level for authorization, mostly role-based access control. So this leads us already, or this brings us already to KCP, a cloud native, a product under the Cloud Native Computing Foundation, which describes itself as a horizontally scalable control plane for Kubernetes style APIs. So in short, KCP extends the Kubernetes API server to be able to host multiple logical clusters on a single shared infrastructure. So instead of separation like here in a common hosted control plane architecture, where you would have for each control plane a separated or its own data store and its custom resource definitions, so API extensions and authorization model, KCP changes that to a shared data store with logical clusters on top of that, with its own authorization model and its own API extension possibilities. These logical clusters can be treated as a Kubernetes API server then in the end. With that, let me introduce another name wording from KCP. It's called workspaces, and workspaces have a one-to-one relationship to logical clusters, which we saw in the slide before. So this as an isolation unit. They are not similar, but they have a one-to-one relationship, and we can use workspaces instead of logical clusters for our isolated units in the next steps. Okay, with that, let me give you the explanation of a workspace in KCP. So a workspace is the unit of isolation for multi-tenancy in KCP. And a workspace has its own available API resources. And the objects are not shared across other workspaces. And we have a delegation of administrative permissions to workspace owners. And they are very cheap because, as we saw in the slide with the logical clusters, we don't need to spin up any resources to create another workspace. So, and to make it clear, a workspace can be accessed as like a Kubernetes API server via kubectl with, yeah. Okay, with that introduced KCP and also the workspaces and the general idea of KCP, let's move back to our tenant-aware API platform here, like this. So now since we introduced KCP and also workspaces, we can replace our generic naming of a tenant-aware API platform with KCP, and we can also replace the texts in the boxes with workspaces, so that we have now in the middle our KCP, and we have a workspace for each consumer, which is similar to a tenant. With that, let's bring the missing pieces of the puzzle into this picture. So at first, we need to have a way how we can bring our virtual machine APIs into KCP, because when we want to share them, we first need to store them somewhere to be able to share them then to other to workspaces for tenants. So where are these APIs for KubeVirt virtual machines intended to reside in KCP? For that, we can also use a workspace. So let's introduce another workspace called provider workspace. And yeah, this can be used to store the API schemas from multiple KubeVirt clusters, which then should be needs to be connected to this workspace. So the next question is then, how do these APIs actually make their way into the provider workspace we introduced before? For that, KCP gives us an API sync agent, which needs to run in each KubeVirt cluster. So like this and that, we have an API sync agent in each cluster, which can export the API schemas from the virtual machines to the provider workspace. So that we can aggregate them in KCP. Yes. So, but we still do not have any way to share them then to our tenant or consumer workspaces. So because they are fully isolated, we need a way to share them. So how can we achieve this which I added here with the question marks, that we can bring the APIs from the provider workspace where we stored them to the consumer workspaces. For that, we would need something where we can publish or export them and also bind them or import them. So actually an API marketplace. This can be achieved in KCP by using two built-in APIs called API export and API binding. So we have here now where my cursor is the KCP from before, and we have our three workspaces. On the left and on the right, the consumer workspaces, and in the middle, our provider workspace, which has our schemas from multiple KubeVirt classes with running KCP API sync agent. And at first, we need to create an API export in the provider workspace so that it's available to be bound by other workspaces. And this is then done by an API binding, which needs to be created in each consumer workspace, which should be able to use these APIs. Okay, with that, actually only one question is left, and this is, how does a VM end up in a KubeVirt cluster when we create it in a KCP workspace? And for that, again, we need the KCP API sync agent, or the KCP API sync agent is doing it for us. And for that, the API sync agent is using an aggregation layer from KCP, which is called virtual workspace. So, and this layer can be used by the API sync agent to be aware on which workspaces it should watch to synchronize objects. So that the KCP sync agent is then able to watch and to do stuff in both directions in the end for all workspaces, consumer workspaces, which bound the APIs stored in the provider workspace and exported by the KCP sync agent earlier to the provider workspace. All right, so now we are complete with our picture and we can put the pieces together. And I will first, before I switch to the terminal, I will explain what I will show there. For that, I need to add two small details which are specific to the demo. The first one is that we have namespaces in each physical cluster, which are mapped to the consumer workspaces. So they have a prefix which is globally unique, and yeah, this is used then by the API sync agent to do the syncing to the workspaces. The second one is that how do we now put the APIs from different clusters together? And this is done by a mutation of the API group we are using. So for instance, for the cluster E's, we use an east-kubevirt.east.kubevirt.demo instead of kubevirt.io. And then it will, if a consumer creates such a virtual machine with this API group, the sync agent will see it and will then create a normal KubeVirt virtual machine in the mapped namespace in the KubeVirt cluster. And then we'll sync back the object state over the aggregation layer to the consumer workspace, so that the consumer is able to see the state of the running created virtual machine. And the same can be done for a virtual machine in another cluster called West here in this example, and the group would be called west.kubevirt.demo. And the sync agent in this cluster would do the same as the sync agent in the cluster East, with a unique prefix, creating the virtual machine in a namespace with a unique global prefix, and we'll sync back the object state over the aggregation layer, so that the consumer is able to see the state of the virtual machine. Okay, and we can do it vice versa, of course. And with that, I will move to the terminal, and therefore I need to reshare. I cannot see my Visual Studio Code. Yeah, here. So, okay, with that, switching to the terminal, where we have actually two terminals. The colors here on the left are almost similar to what we used in the slides. So we have a terminal for two KubeVirt clusters, KubeVirt West and KubeVirt East. And we have two terminal for two consumers. So one terminal for consumer 1 and one terminal for consumer 2. With that, let's go to the KubeVirt cluster East to check the API resources, and we will see that we have the normal common KubeVirt APIs present there. And the same so I switch now to the West cluster, and there we have the same resources available. And with that, I will now execute a watch on the virtual machines on all namespaces in both clusters. So this is for the KubeVirt West cluster, and this is for the KubeVirt East cluster then. Wait. Like this. And now let's switch to the workspaces. And there we have other API resources like these, like mentioned in the last slide before switching to the terminal. And we have two groups where we can create virtual machines. And I will go to the consumer 2 workspace where we can do the same. And then, because I'm running out of time, I will now fast create the VMs, and then we will move back to the KubeVirt clusters to see that something happened there. So this is a creation of a, as you can see here, a virtual machine in the East cluster, and this is then on the West cluster. And if we have luck, we can already see that, yeah, that this is in the running state. And we can do the same for the consumer A. So I switched now to the consumer. I need to hurry up. And I hope I did no mistake. Yeah, okay. So switching back to the KubeVirt clusters, we see two VMs, consumer 1 VM, consumer 2 VM East, and they are here prefixed in the namespace so that they don't overlap, even if they use the same namespace. And the same thing for KubeVirt West. And yeah, because I'm running out of time. Deletion works also, but I will move back to my slides to finish my talk then. So with that, KCP and KubeVirt are a great combination for tenant-aware VM platform because KCP workspaces are lightweight means and provide a Kubernetes native multi-tenancy. The sync agent helps with syncing the KubeVirt custom resources from consumer tenants and provides a convenient aggregation layer. And you can also use the KCP platform to provide additional services beyond KubeVirt and still giving a consumer a single storefront. With that, wrapping up, we started with this challenge of the multi-tenancy and VM sprawl, and we ended up in a clean and scalable way for a multi-tenancy VM platform by using KCP. And yeah, so in conclusion, we can use KCP to create a scalable multi-tenancy platform with multiple degrees of freedom. Okay, so 1 minute above my time. Sorry for that. You have 2 QR codes on the last slide. The left one is a QR code which has the link to the demo setup, which you can try out by yourself. And the right one is just a link to the KCP website. With that, thank you. And sorry for taking 1 minute more than actually planned.
Thank you, Sören, very much. It's always nice to see a successful live demo.